should be streaming. Maybe, maybe not. Maybe not. Oh, there it is. Okay, yeah. I had to make sure. So, another draftphysics.com video presentation and such, and whatnot. And so today's subject will be constant forces. So today's subject will be thinking about it. I realized there's really no way to create a constant force without really accepting the existence of something very discrete that has to push at a very high speed to create anything that would appear constant. But the argument sort of is that it's not really constant. Oops. Yeah. All right. So for us to make a constant force, you'd have to argue it's kind of complicated because, say, if you have something that starts at zero velocity and you get it up to, let's say, 10 meters per second. Okay. Now what do? Because you can't be applying a force that's going 10 meters per second, right? So if you had a force that was going 10 meters per second, that is something pushing it, some kind of object that was pushing at the speed of 10 meters per second, then you could say, okay, once it reaches that maximum speed, it's going 10 meters per second, but now you're not pushing. You have to go faster. What the hell is that there for? For there to be, it has to now go. It has to gradually increase the pressure as the object starts moving faster and faster. So, I mean, obviously it would have to start going, faster than 18. It would have to be almost the same idea of what it started with here. And so I don't see a rational way of saying that, okay, I'm going to start with a certain pressure and I'm going to know how fast I'm going to go at the end. And that way I'll know how many units, how to graduate the increase from, where you're accelerating it, because that's what you see is an acceleration to 9.8. It doesn't instantly go 9.8. It has to accelerate to it, and then it has to accelerate from 9.8 to 19.6, and it has to accelerate to 27 or 8 or whatever the hell it is, point whatever. So it has to do it in these gradual steps, and you're saying, well, how can it know how fast it's going to have to go to do that gradual stepping, because I could have the ground at any place, so if this was a dropping force. So anyway, so gravity is sort of a unique force in the sense that the only way you could duplicate it, I would argue, if you were trying to duplicate the effect of the force, is to recognize that the only way you can duplicate it is to create something like a paint sprayer, or some kind of machine that would produce objects that would hit it, and they would hit it at a rate. So no matter what its speed is, the rate at which they're hitting would stay the same, and with each impact they get a certain push. But then you have to have these things moving very fast, because say if they only went 30 meters per second, right, you could understand that once the object reaches 30 meters per second, it can't make it go any faster. So again, you're stuck because now your object's moving faster than the thing's pushing it. And so that won't work. But if you say it's going, 3 million meters per second, all right, now you have lots of latitude. And so you can understand that no matter how fast this is going, it's going so much slower than the speed of the bits hitting it that with each impact it's going to appear to be gaining exactly the same bit of extra motion. And so with each impact it's going to gain the same amount, and it would only be when it's going, it has to go some percentage of the speed of light, like 10 or 20%, before you're going to be able to recognize that as it goes faster, it gains a little less energy from each hit, so that the rate, let's say this is a 9.8 meters per second rate, the rate goes down based on the fact that it's the speed differential between the bits of force and the object have gotten now significantly great enough that you can detect that they're not gaining the same 9.8 per each little hit. So that's the trick of it. So the only way we could make a machine that would produce a constant force. So, I mean, we can't push something. If you try to push something with a constant force, you're going to get into a lot of trouble, because as the object starts moving, you have to keep increasing proportionally the force you're applying. You have to keep making it go as fast as the object, plus that little bit of extra, that little bit of extra, a little bit of extra, a little bit of extra. And that, how could we create that mechanism except to have something going very fast, hitting it in a consistent manner? Now, of course, distance wouldn't matter in this case because it's like a laser beam. All the light isn't diffusing, so all the force bits would be hitting it at exactly the same rate, no matter what its speed, because there's such a huge difference between the 3 million meters per second of the thing's hitting and the actual speed, which is only 30. So it's you'd never be able to detect the difference between going 100 miles an hour and going 1 mile an hour based on the fact that it would technically should be going a little bit slower. I mean, the acceleration should drop, but you can't see the drop because the speed of the object's hitting is so high. So obviously this is just an argument I'm making to point out that you really can't diagram gravity, okay, without recognizing that, the only it's the only physical mechanism we could create to cause a constant force would be very much the same argument, is that the constant force really has to be in discrete bits, and each bit is going a very high speed, and it keeps hitting the object as it's falling at the same rate based on how close it is to the earth. And really what that really means is how dense the converging radiation is. Obviously the argument is that the radiation is coming from all directions at a constant rate, okay, and so when you're in that stream, it just, as you get closer and closer, obviously all these vectors are converging. So the force gets stronger and stronger, and it's the inverse square law. They're converging this way and they're converging this way, and so obviously that creates the inverse square law. But obviously the field in which gravity is the same 9.8 is, wherever it is, 100 miles, I don't know. It's a pretty significant amount of distance you have to travel before the gravity is measurably changes from that 9.8 number. You have to go to the top of a mountain or that kind of thing. Well, obviously they can measure it pretty exactly now, so they can probably tell just a few hundred feet, but that's telling to decimal places. Anyway, so obviously, it just seems to fit that gravity would have to be understood to be some sort of constant force. When you're in a field of constant density, it's not going to make any difference, and it has to be going very, very fast, because we can't detect any difference between when it's going 100 miles an hour, how much gravity per a unit of time it's going to get, versus going 1 mile an hour. It collects essentially the same amount of force because the force is going so much faster. The things pushing are small and they're going very fast. So the impact is essentially the same. The exchange of momentum is essentially the same. And until they start going a very high speed, that exchange of momentum, or that sharing of the momentum, I would argue, because I think the real argument is the little bits of force actually do stick to the matter, the electrons and protons, and that's how they move, is by collecting force. So I could use rain as an analogy. You could think of gravity as a raining force and understand there's more rain coming down from the top than the bottom, and you're a bucket and you're collecting that difference. And as soon as you hit something or touch something, you lose what you've collected, depending on how substantially you make contact and such. So that was basically the theme of the video. So I guess I could just go through some of the arguments that I've already gone over, just pointing out how this works. It's really simple. Why make it complicated for no good reason? And that there is no good reason, there's no good evidence that what I just said isn't true. And yeah, so I might as well make a clarification. I mean, there's so many these little subtle facts that you always have to be aware of. So I made an argument about 3 springs. You could put 3 springs on a wall and have it so you can release 1, you can release 2, or you can release all 3. And let's say you're just going to push a cart. Now, obviously, the argument is let's do it in space, and then we don't have to worry about wheels and the motion caught up in the angular rotation of the wheels. So it makes it a simpler experiment to understand. And so we're going to have a very dense object that the spring is going to be on the other side of, very massive, like the moon. Yeah, that's a good example. Except the moon has, well, it doesn't matter. The moon has gravity, but it's not going to get in our way, and air resistance would be nothing. So yeah, you're doing it on the moon, and you've just set up a nice, very rigid steel structure that's implanted into the moon. Okay, springs, and then you're just going to launch an object, and we're going to ignore the falling by gravity just for the sake of making this video, frankly. Alright, so you do all of that and you're still going to have a little bit of trouble, because obviously when you have one spring releasing, the object's not going to be moving very fast, so it's only going to have one velocity with one spring, right? So one spring will be one velocity, 2 springs will be 2 velocity, right? But that's not true, because the problem is, as it goes faster, it means the springs are going faster. So the faster you get the object to move, the faster the spring has to move to push it. And obviously when it leaves, the spring is still moving fast. So this leaves at 30, the spring is still going 29. So you're going to end up with springs here, the faster it goes, wobbling more. So at 1v, this one spring is just going to wobble a little bit because it's not going very fast. It's only going, let's say, 10 meters per second when the object leaves. With 2 springs, it's going to be going 20 meters per second. But it really won't be, because more energy is going to be left in those springs, because when it got up to about 19 or 18, that's when it left the springs, and the springs were only going 17, and the thing was going 18, so they're not connected anymore. So now the spring's going to wobble more. And then when you're going 30 meters, if you do all 3 springs, you can't really be doing 30, you have to be doing 27 or something, because now the springs are going to oscillate even more, because they're going faster when the object leaves. So it's so it's a technical detail. It's not going to be much of a difference, but it's not, strictly speaking, going to be 1 spring equals 1 velocity. It's going to be 1 velocity, yes, and then 2 springs won't exactly be 2 velocity, be a little less, and 3 springs will be a little more less, but close enough to 3 times the velocity. But it won't be exact, because of this problem that springs are better at collecting energy than they are releasing energy. they can collect energy at any speed. I can push a spring with any velocity I choose to. I can apply an impulse. Now, obviously, it's not any velocity. I can't shoot a bullet at a spring, because it's just going to break the metal. But within reason, I can vary the speed with which I compress a spring. But if I vary the spring, I can't really vary the speed at which I release, because the higher speed at which I release something, the more energy is going to be left in the spring. And you can understand that as, I gave the example in the other video, last video, is that if you throw a ball at a wall, you'll see that the ball comes off the wall and it'll be oscillating. It'll be doing this. And obviously that energy has to be a use. It's using the energy that went in. So the part of the momentum of the ball going in, when the ball comes back, if it's oscillating, that energy is like angular rotation in a wheel. It's using energy you had to put in. So it's stored energy, essentially. It's not very useful. It's not going to be very easy to collect, where the rotation in a wheel is a little easier to collect. But, similar, but not the same thing. So that's okay. Wow, one viewer. Well, I guess this video might not be worth the trouble. It might not be worth hanging around for any comments or such. So I probably should have just made a regular video. So I guess maybe that's what I'll go back to for a while. So what else? What's the night? Yeah, it's a Monday night. Guess Mondays are not very... it's not the same number of people around. Or something like that. Let's see, so I really need to go into anything else. Probably not. Alright, so we'll leave this one as a short video, with which there are no participants to interact with at this time, so we'll just surrender and say, yeah, we'll try again next time. Alright, so until the next time, and such, and so forth and whatnot.